Right guys, so today we are looking at floating point representation, okay? Now, floating point representation in a computer system is how the computer stores a real number being a number with a decimal point, okay? Now, this is a very similar process to standard form notation in maths, okay? Now, what I mean by that is, in maths, you would take a number, okay? And you would move the decimal point to the front of the number, okay, so you'd move it from here to here to then here to here, and then the decimal point would end here, okay, and you would write the number out with times 10 to the power of how many times the number has moved, okay. So the number 2569.362 would be written like this, okay? So let's make my text box nice and big. So this number would be written like 0.2569362, okay? And it would be multiplied by 10. Right, also my text box wasn't big enough, okay? And you would write down how many times the decimal point is moved, and it's moved 1, 2, 3, 4 times, so it would be times 10 to the power of 4. Okay? Now, in computing, you'll be asked to look at a number like this one, okay, and you will have to identify two separate parts of the number, okay? Now, those parts would be this part here, okay, and the whole number without the decimal point in it, okay? So this number here, okay? Now, this number is called the Mantissa, okay? So the full number without the decimal point, so ignore the 0 point, okay, would be the Mantissa, and this number would be called the exponent, okay? So you could be asked what two numbers make up a real number or a floating point number in a computer system, and the answer would be the mantissa and the exponent. You could be given a number like this, and you would have to identify the mantissa and the exponent, in which case you would write down the number without the decimal point, and then how many spaces the decimal point is moved, okay? Now, the name floating point comes from the fact that the decimal point has floated from the middle of the number all the way up to the top, okay? And the reason we have a need for it is because computers really struggle storing the decimal point, okay? So that is what a floating point number looks like, okay? Right, so the next thing we're going to look at is how we would represent a real number in binary, okay? Now remember, a real number being a decimal point number, okay? So on the screen we have the real number 10.25, okay? Now the way in which we do that is we extend our binary headings, okay? So if with any decimal to with any denary to binary conversions, I'm going to write out the headings first of all, okay? Give myself a nice big box, so make sure that I can fit it all in, okay? So I'm not going to do all the headings start from 1 to 8. I'm actually only going to start at the heading 8, okay? Now the reason being for this is we're looking at the binary and the denary number 10, and to add up to 10 we only need 8 and 2, okay? So I'm going to write 8, I'm going to put a few spaces in, 8, 4, 2, and 1, okay? Now, using what we've learned in previous lessons, 10 would be stored as 8 and 2. So I'm going to write a 1 under the 8, 0 under the 4 because it's not being used, 1 under the 2, and a 0 under the 1. Okay? Now, that is how we represent the 10. Now, we need to represent the 0.25. Okay? Now, how we do this is like so, okay? We need to extend our binary headings. Now, if you remember, 1 is 2 to the power 0. 2 is 2 to the power 1, sorry. 4 is 2 to the power 2, and 8 is 2 to the power 3. Okay? Now, if we put in a decimal point here, okay, so there we have our decimal point, we are now moving to the right of the decimal point. Now, I know you'll remember this from maths, but if you go a number below 0, so if you take away 1 from 0, you get minus 1. Okay? Then you get minus 2, minus 3, minus 4. So you get negative numbers. Okay? Now, when you put this into your binary headings, so when you do 2 to the power of minus 1, okay, you get a half, or 0.5. Okay? So, to make it a bit easier to see, I'm going to write a wee half above it. So you know that it's a half. Okay? Right? Now, once we've done a half, it's the same as before. We double, but this time we're doubling the 2. Okay, so after a half, we get a quarter, and a quarter is 0.25. Okay, then after a quarter, we've got an eighth, which is 0.125. Okay, so that's a quarter. Again, can only apologise what we're writing, and this is an eighth. Okay, so if we put our full stop here, okay, 10.25 in binary is 1010.010. Okay, 1010 being 10, and this here being 0.25. So this is 10.25. Okay, and that is how we extend our binary headings. Okay, so again, we're just, instead of doubling, we are halving each time we go along. Okay. Right, now we're going to continue to convert this into a floating point number, and we're going to get the mantissa and the exponent. Okay, so I'm going to put my wee headings, going to write mantissa here, and then another heading for exponent. Okay. Now, the way in which we turn this number here into a floating point number is we move the decimal point. Okay, like I said before, move the decimal point from there to the front of the number. Okay, so this number here becomes 0.101010. Okay, now, and that number is our mantissa. Okay, because remember, the mantissa is the full number without the decimal point. Okay, so 101010, okay, is our mantissa, and because our decimal point is moved 1, 2, 3, 4 places, our exponent is 4. Okay, but because this is a binary number, okay, we're going to convert that 4 into 100. Okay, because 100 is 4 in binary. Okay, so if you were to write this number out as a binary floating point number, then the number would look like this. Okay, 0.101010 times 2. Okay, now again, I'm going to make this bigger so that it's easier to see. So it'll be times 2, and it'll be to the power of 100. Okay, and that is your complete floating point number. So that is 10.25, and how it will be represented using floating point, and it's going to be stored in the computer as the mantissa and the exponent of 100. Okay, right, and the last thing we're going to look at is how we take a floating point number and how we convert that to a real number. Okay, now here's an example of how it can be written in a test or an exam, but in the actual sheet you're going to be looking at, this will be very similar to the last question. Okay, so the first thing you've got to do is you've got to convert this number, this binary number, into a denary number. Okay, so to do that, it's the same as usual with your binary to denary conversions. So you write your heading, so it'll be 1, 2, 4, 8. Okay, so this is times 10 to the power of, and it's 10. Okay, so 8 plus 2. Okay, 1, 2, 4, 8. Yep, definitely 10. Okay, so what you would then do is you would move the decimal point 10 places to the right. Okay, so in this example, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those two numbers don't exist. So this number would be 2, 3, 5, 6, 8, 6, 9, okay, and again, it's moved, so if we count again, so move from 1, 2, 3, 4, 5, 6, 7, okay, to get to the end. So we need to move it another 3 places to the right. So what we do is we add on 3 zeros. So 1, 2, 3. Okay, so this number here, 0.235869 times 10 to the power of 8, is 10, sorry, is the same as this whole number here. Okay, and that should help you with the floating point sheet too. Okay.